this is another, I will say this is an hypothesis. So this is something that we are trying to claim. It might be not true. Okay, let's try it. So we are saying, hey, RISC-V community, or let's say maybe better, open source hardware community needs peripheral. So by that I mean the following. So IP vendor, when you try, when you try to approach an IP vendor, you know, you're like looking for, let's say, a PLL. That vendor will give you a PLL that is not close to what you want. Why? Because that vendor just had the IP because he did it for another customer who had different kind of specs. So then this vendor is going to ask you, okay, it's fine. I can give you that IP. I'm going to change it for your specs. I'm going to charge you this. So it's going to cost money. Wow. Okay. There are some standards right out there like FIs, like USB, LPDDR, PCI Express, AMBA, but no other standard for a different circuit for clocking, for instance. So I just mentioned, right? So you want a PLL. Okay, you need this space. Why you need this space? Because you just want this space, right? And then this guy has another specs, and they'll go on, right? So then it's costly. So what about standardizing a PLL? That's gonna be cool, right? Because so that's one thing. Biasing, same thing. GPIO, yeah, you will be surprised. You will buy a chip, a microcontroller, which is supposed to be commercial microcontroller, supposed to be for the similar application, the same application. You will find out that those guys have different driving current and even speed. It's kind of fun to see that the industry is not quite not talking. So, for instance, a simple power reset can hit your pocket. Why? Just because they have the power. Right? Okay, you had tested, had silicon proven, you want it. You don't want to risk a lot of money. Okay, I know you. If you don't get it, you are risking a lot of money, right? So then you just have to put money to buy a power and reset. See, power and reset is quite simple circuit. So there is another IP that is quite expensive too. Buses IP are there, but expensive. Why? Again, it's a similar idea. Just think about compilers in the decades ago. They were charging a lot of money. So once you have the offer, then they can be free. So can we do better? We might. We do believe that we might. So this is the agenda. Why we need more? So I will try to make a case why we need more open standard silicon hardware. And then I will jump to why IC community can build up peripheral. So I will try to show our case. And then at the end, I will try to give a suggestion. So what should be our next step? So this is the first case that I wanted to put why we need it. So we know all this bottleneck, right? The communication bottleneck. We have plenty enough resources for computation. Even though you have RTL, just push the button, you have a processor right there. But what about getting data in and getting data out? Like you want to process a high density image. Okay, how are you gonna get in that data? It's funny, right? Like for instance, the LowRISC Endeavour. The LowRISC Endeavour, okay, it's quite hard to build. These guys, Google guys, are asking for a 64 SLC, but there is too many difficulties to doing that. Clocking circuitry, high-speed interfaces. Let me give you an example. Just Altiva guy, right? Andreas Olofsson. He just taped out 1,000 core. You know how he get in the data and out? He decided, I don't have IP, so I put 1,000 I/O. And how much speed he's running in this I/O? 150 megahertz. I don't know. I guess he has to pray a lot if he's gonna run all of this I/O at that speed. You know that old signal integrity thing, right? So yeah, definitely need SPICE there. So the second case, Linux drivers are still a pain in the butt. You will be easily found articles, titles like this, 11 reasons Linux sucks, and you will read it. Hey, I had it. I had this experience. My sound card drivers from my laptop and graphic drivers, they don't work. So you go and check. Okay, there is a reverse engineering driver, but I cannot get the 5.1 feature from my sound card. So what we should do about it? So we should standardize as much as possible. So for instance, we saw in the previous workshop that NVIDIA is trying to replace their controller with a RISC-V core controller. What is the advantage of that? First, the big advantage for them is a lot of flexibility for next projects, but also drivers. So you will be able to have the community to develop drivers. Why? Because this is translucent for everybody. Register abstraction, and as I say, also for all the analog circuitry, you should also have kind of additional circuitry. So you will see this kind of why this driver with this sound card doesn't work, because they have analogous circuitry that need register to change the registers, and those are obscure. So that's why they don't work. So we should try to open to have kind of a standard peripherals. So we know all this might translate in quality drivers. So again, I think that this example I already mentioned it. We don't have any GPIOs. We are kind of easy circuitry to design, but you will not say, okay, how much current I should put? How much? I mean, it depends on the application. Okay, let's check automotive. So you go on automatic, even though all the chips are different kind of current switching speed and current driving. Okay, so this is our case of showing that we are able, the community can able to develop IP. So we have done some. So we have decided to go through using AMBA buses for the microcontroller that I just presented in the previous. We decided to go RC4 and LPDDR3. Why? Because this is the most popular out there. So you know, maybe you have a RISC-V core and you have these buses well tested. So these companies decided, hey, instead of paying license to ARM, let's just put there on a RISC-V. It works with our peripheral. That's why we decided to go that way. And this is open standard. It's from ARM, but it's open standard. So we are developing accelerator scores on those based on these buses. So in this in the tape out that we did for the microcontroller, we put a SAR ADC. This SAR ADC, we try to synthesize it completely. But in order to get speed, you need a high-speed comparator. So of course you don't have comparator in the standard set. So we went there and to handcrafted a comparator to get high speed, like a strong ARM comparator. So even for the CDR and PLL, so we are trying to do synthesized CDR and PLL. Actually, here on the lower left corner, you will see kind of the approach that we're taking. We start from RTL, we synthesize, but like the DCO, right? The ring oscillators, you cannot go and let the tool decide what kind of ring oscillator is going to synthesize. We just put an list there. And also we put constraints for that list when the flow is doing the place and route. So we had to put out. It's working. A CDR and a PLL. We are soon publishing some results in academic conferences. So here is the so this is another endeavor that we are into. We are trying to build USB 3.1 generation 2. That means 10 gigahertz per second, 5 gigahertz. An IQ is at 5 gigahertz. We're talking about 25 dBs, including the loss also from the connectors. So you have to develop a lot of analogish circuitry. The PCS part of the USB is already cracked. We already tested. Now we are working on the Analogish Front-End. The Analogish Front-End is totally analogous. So don't expect you will get RTL code there. But we are doing it. We are working hard to get this done. This is kind of the architecture of what we are doing for the USB 3.1. We also going further. So to test this, I mean, to go and check every node, kind of the quality of the signal, you need ChipScopes. You know, the one the Virtex 6 and 7 they have. It's not that difficult to build a scope there to check that. So we have done it, and it's working fine. Actually, we already submit papers that are accepted. We also doing offset correction different than people is doing it. We are using phase instead of voltage or current to do the offset correction. Here are some measurement samples where you can go and check the ChipScope, like just you can see these kind of tools in the Silence and Altera tools, right? Where you can just go ahead and say, okay, you're gonna see the phi signal there. You can do offset correction on fly. Okay, we also build PRBS generator and checkers in order to get high speed in order to test these guys. So in order to get that speed and get it done by RTL, we had to handcraft the flops. So we just went from regular pass gate flops all the way to kind of dynamic flops through single phase clock flops. Hey, we also doing LPDDR3. So we are trying to, so PCS is cracked too, so it's already done. We are also in the right side hand of the slide, we are also doing the UVM IP. So we are comparing to the UVM IP that is there obfuscated and encrypted by, you know, the AD tools guys. But we are doing it, we are comparing it there, we're getting it close. You cannot say that you have a PCS working if you don't do a good verification. So you are releasing something, you have to put the UVM too. We are also doing security circuits. Why? Because you have seen it, right? Plenty of presentations yesterday about why we should care about security. So you saw yesterday that it's changing keys, and you know, it's a pain. Typical way is synchronous establishing keys. We are doing it. So what's the problem with this? This is, you're using software, it's a large computational cost. If you are using hardware, the large footprints and power is bad. So even for microcontrollers, for an IoT thing, you cannot do this. But we are also cracking it. We are trying to put a lightweight mechanism using 3-parity machines. This is using neural networks. So we can do exchange in an open wire without the bad guy trying to get us, because it's just we are changing weights, not just that. So we tape it out, we test it, it's working. We also, of course, you have security. I mean, for that tipping, you need a true random noise generator. So we have put a true random noise generator. We took the idea from Michigan guys, the idea of the general idea, but we saw that the results were so biased, so we decided to do some post-processing. After that, we do this, where they say that box that says rule X is about automatons doing this post-processing to improve the biasing of the number generator. We tape it up, it's working. It's fully synthesized, by the way. So we are going beyond. We also don't have this microcontroller that we put it there. We don't have no volatile memory. So that means we don't have EEPROM. You know, in order to hit EEPROM, you need additional mass. That means additional cost. You need to have 2 gates. So there are some IP there that works in single gate CMOS, like regular CMOS. But it's expensive and it's hard to get it. The Synopsys guys got it. So we decided, okay, no, we might find out a way to do it. So we went there, check patents, check articles, check papers, say, okay, there is something here that we can do better than them, and try to check it. Problem with this, you don't have the modeling because it's quite different, right? You are pushing the devices in different way. You are tunneling them. You don't have those models in the PDKs. So we went out there with the foundry guys, asked them, no, we don't have anything. So we decided to tape out 128-bit cells with different sizing, aiming to get kind of a modeling a stats number from there to get a way to model. Good thing, we got a couple of them, 70 cells of them working. Now we believe that we have kind of way to go better in better density, for instance. We also tape out a charge pump. Here are some measurement results in order to get the speed that we require to write and erase those cells. Okay, here is the last part of my presentation. So here is one thing that I'm putting here is a suggestion. So what we should do, let's imagine a table where the community, some place like the Free Chips project, where there is something like RISC-V recommends this kind of IP, right? So this the kind of what kind of, like, for instance, the SPI. Okay, was used by Epiphany 5, Rocket. It was there is functional model. That means that you can do verification. There is silicon point, so that kind of things we should have. This is kind of a suggestion that I have. We should build that. To end my presentation, these are the takeaways. Don't get your system on machine idea start just because you don't have regular IP. We also need more standard peripherals. Like I say, we need to go and standardize things that are not standard. Please don't reinvent the wheel. We need to join efforts. Thanks.
Questions for Elkim? People just want to leave. Oh, you have a question. 2 questions.
Megamox Sci-Fi. So for the analog IP, how tied is what you're doing to the library? And do you think that we need to agree kind of on some libraries that we're going to focus on if we're going to design for fields?
That's a pretty good question. The analog circuit is tied to the library. There's no way. I mean, when we are saying fully synthesized, it's not tied to the library, right? But when it is, I mean, like the comparator that we did also to put in there in the flow, is tied to the library. You need to develop your standard cell, do it properly to put in the flow, right? So that's completely handcrafted. So it is tied. How do you release this? There is an issue, but we have been discussing. I mean, you have an NDA with the foundry, and even with the foundry, and I know that you have an NDA, I can release it to you because I mean it's able, but I cannot give you right away the layout. I can give you schematics, but I cannot give you, for instance, the layout. So, yep. Hope that answers your question.
Tommy Thorne from Esperanto Technologies. I was curious about what, if you could expand on your security efforts. You were saying you're doing a crypto engine. What is it supposed?
No. I mean, there are plenty of people doing crypto engines, but there is not many people doing establishment keys communication. So we are trying to, we are not focusing on things that a lot of people is doing. We are thinking like, say, wow, these guys haven't think about this. So we're doing that. To random noise generator, few people do it. Intel, we compare small, some schools, but there are not there like open. So we are kind of checking around and see what there is now there and try to fill it.
Anybody else? No? All right, thank you.
Yep.